All right. Okay, let's go back to mathematics or physics. And do a little more work. So, so the first bit that I wanted to do specifically on inhomogeneous equations is let's ask what happens if the force that's applied is an exponential force, right? So let's say that it's some constant times e to the mu t, right? So I've already done this for one-dimensional equations. How to handle things like this. So let's see how to handle them in multi-dimensions. Well, this is about calculating the particular integral, and you see that the particular integral up there is that integral from 0 to t of r dot e dot r minus 1, etc. Right? So let's see how to calculate this, specifically for this force. Well, so the particular integral then, as a function of time, is integral from 0 to t dt prime r dot, well, let me write this matrix as diagonal matrix E of e to the lambda I t minus t prime dot r minus 1 dot f, right, so this force, and times e to the mu t prime. Well, this is just r, so r I can take out of the integral because it's constant. This r minus 1 dot f I can also take out of the integral because it's constant. And so what I'm integrating is the diagonal matrix containing lambda I e to the lambda I t plus mu minus lambda I times t prime. And all of this dot r minus 1 dot f. But of course, integrating the diagonal matrix is the same as integrating each of its elements and putting all that on the diagonal, right? So this is the same as the diagonal matrix e to the lambda I t integral dt prime from 0 to t e to the mu minus lambda I t prime. This integral is easy to do. So, so this is just e mu minus lambda I times t minus 1 divided by mu minus lambda I. And so stacking it all back together is r dot, and then on the diagonal, what do we have? So e to the lambda I t times this gives me e to the mu t minus e to the lambda I t divided by mu minus lambda I, and then dot r minus 1 dot f. So that's the particular solution, right? And so there is nothing particularly special to things having to be done in n dimensions. you might worry, what if mu minus lambda I is 0? Well, what if mu minus lambda I is 0? Well, there are there are two ways of doing this. So one way of figuring out very, very quickly what happens if mu minus lambda I. This is a n-dimensional case of the situation when we try to force the system at a rate which is equal to one of its eigenvalues. Okay, so that's the story with this. Well, e to the mu minus lambda I t minus 1, mu minus lambda I. Let's consider what this does, and then times e to the lambda I t. Let's consider what this does when mu minus lambda I is not 0, but is very small. So let's take it to plus 0. Well, if we take it to plus 0, we just expand this exponential, right? So this is e to the lambda I t, mu minus lambda I t. So this exponential is 1 plus this and minus 1. That's all I'm left with. Divided by mu minus lambda I, which cancels. And I get t e to the lambda I t. And there you go. I've got myself a solution which you probably could have guessed, right? I mean, you already know that if I force something with a force that's equal to, that's exponential and has one of the eigenvalues of the system as its rate, then the solution is going to be t times that. Okay? So, and indeed, the solution is t times that. Right? There are a million other ways of proving it, but this, I hope, is sufficiently convincing. So, well, now you can have fun trying to generalize this to trying to see what happens if you have polynomial forces and you know, forces that combine polynomials and exponentials and so on. But this language pretty much allows you to push it all through without much additional difficulty. Let me address the question of what happens. So far, right, what I've shown you is what will happen if it is possible to find n eigenvalues of a matrix, all of which are different, right? It was important. They had to be non-degenerate. Because it turns out that only in that case can I prove, in general, that there will be n eigenvectors, which are all going to be linearly independent, form a basis, and therefore I can do all the things that I have done, right? What if not, you might say, right? What if, for example, I end up with you know, I solve the characteristic equation, determinant of a minus lambda equals to 0, and find lambdas, not all of which are different from each other? Then, you know, do you give up? The question, of course, the answer, of course, is of course not. I mean, we never give up. So there is one particular case of systems for which dealing with this is particularly easy, right? And those are Hermitian matrices. So Hermitian systems. Well, so again, we consider an equation that looks like this. So the homogeneous equation. And we ask what happens if the matrix is a Hermitian matrix. So A is equal to A dagger. Let me remind you that A dagger means A star transposed. So you've had that possibly even, well, what was it, last week or something like that? You know, when was the, maybe a bit earlier. So there's a, what happens if that's what it is? Well, first of all, things become much easier in terms of all these transformations. So now if these are right eigenvectors, meaning A dot Vi is equal to lambda I Vi, then, well, let's see what then. Let me take star of lambda I Vi. Well, star of lambda I Vi is A star dot Vi star. But A star for a Hermitian matrix is A transposed. And A transposed dot Vi star on the right is the same as Vi star on the left dot A. So that means that Vi, so if these are right eigenvectors, then the complex conjugates are left eigenvectors. So for a Hermitian matrix, once you've determined the eigenvectors, the right eigenvectors, you get the left eigenvectors for free. But that means that, remember that R minus 1, I showed you that R minus 1 was a matrix whose rows were the left eigenvectors, right? Well, that means that, and R was the matrix whose columns were the, sorry, R minus 1 was the matrix whose rows were the left eigenvectors, and R was the matrix whose columns were the right eigenvectors. And, and so knowing this, therefore means that R minus 1 is R dagger. Right? Because in order to get R minus 1, all I have to do is take the columns of R, take the star of them, and turn them into rows, which is the same as transposing the matrix. Okay. So R minus 1 is R dagger. Well, you see here that the left eigenvalues are the stars of the right eigenvalues. But I've proven to you earlier that the right and the left eigenvalues are the same. Right? That means that lambda I is equal to lambda I star. So lambda i's are all real. That you probably already know, that the eigenvalues of a Hermitian matrix are all real. Now, if lambda I is not equal to lambda j, then the corresponding eigenvectors of a Hermitian matrix are orthogonal. Do you know that? Did you know that before? Yeah? I see sort of tentative nods. But you know, that is in vectors and matrices, right? Then Vi star dot Vj is delta Ij. Okay? So Vi are orthogonal. So this basis that we have, in which A becomes diagonal if all the lambdas are different, right, is not only just a basis, it's actually an orthogonal basis. Now, in the particular case, when the matrix is real, right? So when A is real, which is a very important particular case and kind of prevalent in applications, A dagger equals to A is the same thing as A transposed equals to A. So the matrix, so Hermitian matrix that is real is symmetric. This then means that the left eigenvectors are actually equal to the right eigenvectors. Right? Because there's no starting anything. For a real matrix, I should be able to get real eigenvectors. And so then R minus 1 isn't just R dagger, it's just R transposed. So the transformation that diagonalizes our matrix, so the diagonalizing transformation, is a rotation. Vectors and matrices, homework number 3. Right? You'll see that that's a matrix whose inverse is its transposed is a rotation. Right? So what this says is that if the matrix is Hermitian, even if it's not in a diagonal form, if you're able to find n eigenvalues that are all different, and the corresponding eigenvectors, that instantly gives you a matrix that will just rotate you into a system where everything is diagonal and the evolution along all the directions is decoupled. Furthermore, if lambda i's are not different, meaning that some of them are degenerate. Let's say you've solved the characteristic equation, you obtained n solutions. Obviously, determinant of a minus lambda 1 minus lambda equals to 0 is always an nth order polynomial equation, so it'll always have n solutions. Right? There's no problem with that. But the restriction so far has been that these n solutions have to be all different. Right? So now I'm saying, suppose they're not all different, right? Some turned out to be degenerate. Then what? Well, for Hermitian matrix, it is then possible to prove that A can still be diagonalized. How is it going to be diagonalized? Well, basically, what will happen is that suppose some value lambda occurs k times. Right? So let's say lambda has a degeneracy k. Right? Well, that will mean that vectors that solve this equation with that lambda sit in a k-dimensional subspace of the linear vector space that you're living in. So solutions of this sit in a k-dimensional subspace of the vector space. And if you can prove this, I won't go through the proof carefully, but what I want to say is, I think it's actually fairly intuitive. So and then so these sit in k-dimensional subspace. All you need to do is take an orthogonal basis inside that k space. And that gives you k vectors, all corresponding to the same lambda, right? Which are all linearly independent and indeed orthogonal. right? And that's the subset that you have to insert into your basis, right? So in other words, the way to diagonalize a matrix with eigenvalues that have degeneracy is just to isolate groups of roots that occur a certain number of times, and for each root which occurs several times, just find several orthogonal vectors that all satisfy this equation. And you can prove that it's guaranteed that they will always be there, and also that all the rest are going to be sitting in a subspace that's in a subspace that's orthogonal to this subspace and completes it to the total. So now you might say, but how will the corresponding solutions to the linear equation be linearly independent if they all evolve at the same rate, right? Because they all have the same lambda. Well, they're linearly independent because they evolve at the same lambda, but in different directions, right? Because they multiply different vectors, they're still linearly independent. So for Hermitian matrices, basically the occurrence of degenerate eigenvalues is not a problem at all. You just go ahead and you still find these eigenvectors, and everything works in the same way as I have just described, right? Because if you go back to this whole construction that I have presented to you, nothing there actually depended on lambdas being different, except the guarantee of the existence of the v's, of the eigenvectors. Right? So the important thing was to get a basis, right? If the basis was there, we knew what to do, right? Lambdas would, are, and indeed that it's also the case that if the matrix is not Hermitian, and some of the lambdas are degenerate, but it so happens that you can find for each degenerate lambda the right number of eigenvectors, that's still fine. Everything that I've said still applies, right? So the difference between general matrices and Hermitian matrices is that for Hermitian matrices, I guarantee to you that you always will be able to find the right number of eigenvectors. For general matrices, not necessarily, right? So now let's talk about, so that's, that's that. When you're dealing with Hermitian systems, there's absolutely no problem, and keep going in exactly the same way as I've described. However, unfortunately, it's not the case that we can always just look at Hermitian systems. There are non-Hermitian systems. They're quite important and have to be handled. So now let me give you an example of a non-Hermitian system. So non-Hermitian systems. So that example is actually one that's occurred before. So let's consider a scalar nth order differential equation. So consider this equation. Right, so that's just, so for n equals to 2, that's the equation on which we spent 2 hours last week. Right? So, well, how do I apply what I have just said to this equation? Well, I have to turn it into an n-dimensional system of equations, right, in order to do that. How do I do this? Well, I introduce new variables. So let pi be the ith derivative of y, and this will run from 1 to n minus 1. So these are n minus 1 new functions. Then I can rewrite this system of equations in the following form. So what does this tell me? This tells me that Pn minus 1 dot, that's this, right, is equal to minus a n minus 1 y, well, let me first do it like this. Y n minus 1 minus etc. minus a1 y dot minus a naught y plus f. P dot n minus 2, well, that's by definition Pn minus 1. Pn minus 3 is Pn minus, the dot of Pn minus 3 is Pn minus 2, etc., right? And I get to P1 dot is P2, and finally y dot is equal to P1. And these guys here, of course, are Pn minus 1, this is P1, etc., right? So that's how I turn this into an n-dimensional system. Let's write this in matrix form. So it's d by dt of Pn minus 1, Pn minus 2, all the way down to y. And that's supposed to be some matrix dot Pn minus 1, Pn minus 2, etc., y, plus, so, okay, so what's in the matrix? In the matrix, I just read it off here. It's minus an minus 1, minus an minus 2, etc., minus a naught. There is a typo in my notes. It should be minus a naught, not a naught. So now, so that's the first line. That's the first equation. Pn minus 2 dot is Pn minus 1, so there is a 1 here, and then zeros afterwards. So, etc., right? And there will be 1s like that all the way down to the bottom of this matrix, and there is a 1. So this is under the diagonal, right? And then there are zeros everywhere else. Plus the force, which is just F0 and so on. So this is our matrix A for this equation. So it's not particularly difficult to see that A minus lambda 1 equals to 0 is the same equation as lambda n plus a n minus 1 lambda a n minus 1 plus etc. plus a1 lambda plus a naught equals to 0. So in principle, if I could solve this equation, right? So this is my matrix A, right? If I could solve this equation, then I learned that the solution is sum over I ci e to the lambda it, right? So by exactly the same argument now that I've given you in general. But will all these lambdas be the same? Not necessarily. Is this matrix Hermitian? No. Right? It's not Hermitian because it's manifest, well, let's say A's are all real, right? This matrix is manifestly not symmetric. Right? So actually, you know, if you can find the right number of lambdas, then great. Congratulations. But if you can't, it's not necessarily clear what to do, and it's not guaranteed that you're going to be able to construct a basis in the n-dimensional space, and therefore the solution. So the question then is, you know, what is then to be done? Well, and what is then to be done not just with this matrix, but with any other matrix that also has this general form. Right? So there are, one can imagine plenty of systems with non-symmetric non-Hermitian matrices that do not necessarily reduce to an nth order equation. So how to handle them? Well, how to handle them is there are two ways of handling them. One slightly more intuitive than another. So the first way of handling them is by a mathematical result known as Schwarz Theorem. So what Schwarz Theorem guarantees to you is that for any matrix A, there is a unitary transformation, meaning there is a unitary matrix Now, unitary matrix means a matrix such that its inverse is equal to its dagger. Okay? Such that if you apply that transformation to the matrix, u cross dot a dot u, u dagger dot a dot u, the result will be a triangular matrix, meaning it'll look like this. So it'll have something on the diagonal. In fact, what it will have on the diagonal will be its eigenvalues. I'll show that in a moment. Above the diagonal, it'll have stuff. And below the diagonal, it'll have 0. Right? So the guarantee is that you can always find a unitary transformation. So this u, right? That will turn your matrix into a triangular form. So these things here will be its eigenvalues. Well, first of all, how do I prove that they're eigenvalues? So determinant of A minus lambda I. Let's calculate determinant of A minus lambda I. That's determinant of u. Oh, so let me call this matrix T. So that's determinant of u dot T dot u dagger, right? So why is that? Well, A, clearly because u dagger is u minus 1, this means that A is u dot T dot u dagger, right? Just dot this thing on the left with u and on the right with u dagger, and you'll get this result. So minus lambda, and I can replace the unit matrix with u dot u dagger. But that's determinant of u t minus lambda dot u dagger. But that's determinant u dot determinant this dot determinant u dagger. So it's determinant u dagger, determinant t minus lambda. These two cancel because determinant of the inverse matrix is one of the determinant, right? Because u dagger is u minus 1. And so this is determinant of t minus lambda. And now calculate the determinant of that matrix. Right? Because there is nothing under the diagonal, if you start from below and start expanding the determinant, you will find that this is simply lambda 1 minus lambda dot 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 lambda n minus lambda. And so setting this to 0 is the same as setting this to 0, and so lambdas are the eigenvalues. Okay? So, right, suppose this can be, well, actually not suppose this can be done, right? That's what the theorem says. So I won't go through how it can be done, but it's reasonably easy to do. So that's again in my notes I explained how to do it. But let's for a moment accept that such a thing can be done. If such a thing can be done, what can we conclude from this? Well, let's take our differential equation and see what happens if we substitute this triangular decomposition into it. Right? So put the triangular decomposition into it. This will say u dot t dot u dagger dot y. Now multiply the whole thing by u dagger. This gives you d by dt u dagger dot y is equal to t dot u dagger dot y. Well, so clearly we have triangulated our system, right? Let me call this Xi. What we have found is that Xi dot is equal to triangular matrix dot Xi. So if we take our matrix, find the unitary transformation that turns it into a triangular matrix, we can then apply that transformation to the whole space of vectors on which we are working and turn our differential equation in our system of differential equations into a triangular system of differential equations. Right? Remember, to recover original y from that, all you need is just to dot Xi with u. Now, what does this look like? Let me actually write this down explicitly. D by dt, this is Xi1, etc., Xn. And that's lambda 1, T1, 2, etc., 0, lambda 2, etc., and so on, right? All the way down to lambda n. These are all zeros, dot Xi1, Xn. But this can actually be solved, right? Let's start solving it from the bottom, right? The last equation is Xn dot is equal to lambda n Xn. Huh? So that means that Xn of t is equal to some constant e to the lambda n t. Well, what's the penultimate equation? It's Xn minus 1 dot is equal to lambda n minus 1 Xn minus 1 plus whatever element of t sits in there. So the element of this matrix, which is n minus 1 n, times Xn. But Xn we already know. So now we have a linear equation for Xn minus 1 inhomogeneous, right, with Xn that we've already found. Well, that's what I was explaining at the beginning of this lecture, right? How to deal with an inhomogeneity that has an exponential form, right? So the solution of this is just a linear equation, right? So we can solve it completely. So the solution of this is Xn minus 1 of t is equal to the solution of the homogeneous equation, which is e lambda n minus 1 t, plus a particular solution corresponding to the exponential force. That particular solution is, well, it's the force times that constant and divided by lambda n minus lambda n minus 1. Right? You can check that this works. Or compare it with what we were doing there. Unless lambda n happens to be equal to lambda n minus 1. Now, what if so if lambda n is equal to lambda n minus 1, well, then you know what to do, right? Then you take, as usual, right? You take this thing and you replace it with t e to the lambda nt. So that's the n minus first equation. What about the n minus second equation? Well, the n minus second equation is equal to lambda n minus 2 xc n minus 2 plus the triangular matrix element n minus 2 n minus 1 times xc n minus 1 plus triangular matrix element n minus 2n Cn. But we already know this one, and we already know this one. So this is, again, a linear equation. Right? So keep going. Right? This is a right-hand side. Solve this equation with this right-hand side and keep going until you get to the top. Right? So this says, basically, if we can turn our system into a triangular system, we can always solve it. Right? Now, how to do it? Again, there is a systematic way of doing it, which is in my notes, but actually, I put it to you that you don't need me to explain to you how to do it, because you've done it many times. This is what in linear algebra is called bringing a matrix into an upper echelon form. Right? Have you come across that? I think you have come across this, right? There's a, what's it called? Gaussian elimination procedure, right? What does Gaussian elimination procedure consist in? Adding rows of the matrix, right, with various coefficients, right? So you've already done this when you solved linear systems, right? You've done this many times. You've added rows in such a way as to turn everything into upper echelon and then solve everything. Well, the same is done for differential equations. So that's so that's one way of handling it. And because Schwarz theorem is provable and indeed proved in my notes for a completely general matrix, you are not this is a great moment, right? Because this means any linear, any system of linear ordinary differential equations can be solved explicitly, always, right? So you can be, so you know, you should never despair when looking at a linear system, right? The moment you get a linear system, the problem is solved. So I should incidentally warn you of the following. So in principle, there's nothing here that stops us from applying this procedure to any matrix, including one that has non-degenerate eigenvalues. Right? So this, I especially said this, this was the remedy if you had some degenerate eigenvalues and the matrix was not Hermitian, right? But actually, this is not just the remedy for that. It's a universal panacea, right? It's a, you can apply it to any system. Now, however, you have to do it carefully, because typically a transformation that will take a matrix to its diagonalized form, unless the matrix is Hermitian, does not have to be a unitary transformation. Right? That R that I had there, right? In general, R to the minus 1 was not equal to R dagger. So now we know that for any matrix, we can have a unitary transformation that will turn it into a triangular form. And we might also have that R transformation that will turn it into a diagonal form. right? So it may well be that you will arrive at the same solution via a different route, which in fact will be much longer, right? So it's always worth finding the eigenvalues first and seeing whether they're all different. If they're all different, then you should follow the procedure I outlined in the first lecture, right? And only if that fails should you go for this, because otherwise you'll be doing quite a lot of additional work. There's no stipulation that the triangulating transformation is unique, right? This just says there exists a unitary matrix, but nobody says that no other matrix can turn no other transformation can turn your matrix in a triangular form, right? So final point. So this is how you do it in principle, and I think this, hopefully this appeals to something that you've already learned in linear algebra, that you can turn a matrix into upper echelon form, and therefore that's your method for solving your differential equations, right? There is actually a simpler method which relies on a mathematical result, which is more powerful but much harder to prove and much less intuitive. So that result is called Jordan's theorem. So let me outline this. So this is a very powerful method for solving just about anything, but as I said, harder to prove. So suppose lambda 1 is a degenerate eigenvalue that repeats m times. Okay? So, and has at least one eigenvector, which I will call V1. Then let me define the following set of vectors, right? Then a set of vectors, m of them, the first of which is that eigenvector. Actually, not m of them, k of them. Let me make it different from that. Where k is less than m or equal. So this is called a Jordan chain of lambda 1 if, so this is how we define them. So this is the statement that V1 is the eigenvector. And then A dot V2 is going to be equal to lambda V2 plus V1, and so on. A dot Vk is going to be lambda 1 Vk plus Vk minus 1. Okay? So basically I take my eigenvector, and then I construct a chain of vectors associated to it by making it a solution to this equation, right? Where the V2 is still multiplied by lambda 1, but I add the previous vector on the side. So these are called generalized eigenvectors. So I'll leave this to you as an exercise to prove that they're all linearly independent. So what what Jordan theorem tells you is that if lambda 1 is M degenerate, meaning repeats M times, then it will have L Jordan chains such that the sum of the numbers of vectors in each Jordan chain will be M. So such that K1 plus etc. plus KL is M. Now, if you now take all these vectors and stack them into a matrix R, so if I now take R and put generalized eigenvectors as columns into it. So what I now do is I take my matrix, I calculate all the eigenvalues. They will in general be degenerate. For each of these degenerate eigenvalues, I can get a bunch of Jordan chains. The vectors constituting these Jordan chains will all sum up to the degeneracy of the eigenvector, of the eigenvalue. So at the end of the day, I will have, for each eigenvalue that's M degenerate, I will have M generalized eigenvectors. Then I take all these generalized eigenvectors for all my eigenvalues and stack them together into matrix R. And what I will then find is that R minus 1 dot A dot R will look like this. It'll be a matrix consisting of so-called Jordan blocks, which I will call J1, J2, etc., and zeros here. And each Jordan block looks like this. So it'll look like the eigenvalue associated with it will be repeating itself on the diagonal. There will be 0 below, and there will be 1s on top, and 0. So it's a, you can see that that's the structure that came out of that Jordan chain. It takes a bit of effort to grasp all this, right? But the basic idea is that it's possible via this procedure. It's not necessarily possible to diagonalize a matrix. But what you can do is you can turn this matrix into some gigantic construction like this, where maybe the same eigenvalue repeats several times. And for all the ones that repeat, there will be 1s on top, like that, and so on. Otherwise, everything will be 0. So you can't diagonalize a matrix, but you can turn it into something that only has 2 stripes, right? The eigenvalues on the diagonal and some 1s here and there above the diagonal, right? And that can be done for any matrix. Although this R transformation doesn't have to be unitary, right? And if you apply this procedure to a matrix with non-degenerate eigenvalues, then this R will be the same as the R that I introduced before, right? And the Jordan decomposition is guaranteed to be unique. Okay? Well, once you have this, it's the usual story. Y dot is equal to A dot Y, and that's R dot matrix in the Jordan form dot R minus 1 dot Y. You multiply by R to the minus 1, you get d by dt of R minus 1 y equals to j dot r minus 1 y. You call that xc. You call that xc. And so your system now looks like xc dot equals to matrix in the Jordan form times xc. Now, these equations then, for each Jordan block, they look like this. Xc1 dot is equal to lambda 1 xc1 plus xc2. Xc2 dot is lambda 1 xc2 what have I done?